Okay, we're going to look at question 4 in the practice questions for gravitational fields. What it tells us is a satellite is in circular orbit around a planet with this radius, 5,200 kilometers, at a height of 1,800 kilometers. And it tells us at this height the gravitational field strength is 4.2 newtons per kilogram. What's the speed of the satellite? So I'm going to start by making sure I've written out everything I've been told. So this is question 4 on the gravitational field practice questions. We're told that a satellite is in circular orbit around a planet of radius 5,200 kilometers at a height of 1,800 kilometers. At this height, the gravitational field strength is 4.2 newtons per kilogram. And what's the speed of the satellite? So I'm going to start by writing out the things that I know. So I know that the radius of the planet. So the radius of the planet is 5,200 kilometers. Its height above the planet is 1,800 kilometers. I'm just going to make a quick sketch just to remind myself of what we're talking about here. So here's my satellite above the planet. And whenever I come to use my equations, I have to remember that it's from the object to the center of the planet. So I'm going to need to add these two things together. I'm also told that G is equal to 4.2 newtons kilometers minus 1. And I'm going to do this question in two ways. So I'm also going to, from the data sheets, I'm going to take the value for the gravitational constant, which is 6.67 by 10 minus 11 newtons meters squared kilograms minus 2. And it's really important at this stage to note this is meters squared, not kilometers squared. Okay, so I've got also looking at my data sheet, I do have an equation for the gravitational field strength, which is here. I do not have one for the speed of a satellite, which we looked at in the previous lesson. And the speed of the satellite is square root of gm over r, where m is the mass of the planet. So that's my first equation. And I have a second equation that the gravitational field strength is gm over r squared. So that would be equation 2. I'm going to rearrange equation 2 slightly because I notice these two are pretty similar. So that lets me know that if I do gr, so I multiply both sides by r, I get g times r is equal to gm over r, which is what this term is. So I'm going to make that equation 3, and I can substitute 3 into 1, and that gives me v is equal to the square root of gr. And now I just have to substitute for the numbers. Now I have to remember that r is equal to 5,200 plus 1,800, so that's 7,000 kilometers. So that gives me that v is equal to the square root of 4.2 multiplied by 7,000 to give me speed is equal to 71.46. Now, what are the units of this going to be? Well, here I'm stuck. Because when I then go to look at the answers, the options I'm given in the multiple choice question are 5.4, 4.5, 2.4, 0.2. So something's gone wrong here, so I need to try and work out what's gone wrong here. And the answer is that the first thing we should notice is that the answer I'm getting here is orders of magnitude larger than the answer here. Now that will give me a clue that somehow I've gone wrong in my units. So let's take a look. Let's remember that we had that the gravitational constant is in meters squared. So here's a little, what's the complication is. This quantity here of g, this value comes from the constant which is in meters squared. So even though from these numbers we don't see a meter in here, we need to use it here. So this stage was wrong. What I should have done is, having noticed that there's meters squared, converted this from 7,000 kilometers into meters. So that gives me 7.0. Okay, so now I redo this. That gives me the velocity is equal to 4.2 multiplied by 7 by 10 to the power of 6. And when I do that, I get an answer of 5,422.2. And what are the units here then? Well, this is newtons kilometers minus 1. This is meters. This is velocity. It's going to be meters to seconds to minus 1. And check that's true by working through the units, convert newtons into kilograms, meters per second squared. Okay. Then I'm going to, when I look at my answers, I see that my answers are in kilometers per second to minus 1. So I need to divide this by 2. It gives me 5.4 kilometers seconds to minus 1. Right. Now that was a bit tricky because I had to notice that I need to do the conversion. We could have done the question in a different way. So we could do it in a way where the use of the units becomes more explicit. And I've got G is equal to 4.2 newtons kilograms to minus 1, and the constant is 6.67 by 10 to the minus 11 newtons meters squared kilograms to minus 2. Okay, and my equations again were, that's the equation for the velocity, and that's the equation for the gravitational field strength. Now this time, what I'm going to do is I'm going to use equation 2 first of all, and rearrange equation 2 to give me that R is equal to the square root of, not R, M is equal to GR squared over the constant. So that gives me a value for M, which is going to be 4.2. And here again, I need to convert into meters. This way it's a bit more obvious because I'm dividing by meters. So I'm going to have 5.2 plus 1.8 and 10 to the 6. And that's all squared divided by 6.67 by 10 to the minus 11. And that would give me an answer of, so that gives me an answer of 3.09 times 10 to the 24 kilograms. Okay. What we could do at that stage, and again, this is one of the advantages of writing it out like this, doing it this way, the long way, is that it's easier to spot the unit conversion. The other useful thing is we've got this answer for the mass of the planet, and we know the mass of at least one planet is in our data sheet, and we see it's also 10 to the power 24, so that gives me confidence I'm on the right track. That seems a reasonable number. So now we work out the speed. So I've got V is equal to, and I substitute in the number 6.67 by 10 to the minus 11, multiplied by 3.09 by 10 to the 24, and that's all divided by 7 by 10 to the 6. I'm getting the square root of all that, and that gives me square root of 2.06 times 10 to the 14 divided by 7.0 by 10 to the 6, which gives me the V is equal to, again, 5,426 meters seconds minus 1. Remember, we put it into meters, therefore the speed is equal to 5.4 kilometers seconds minus 1. Either way, we're getting the same answer, obviously enough. This way is shorter. We just have to remember the implicit use of meters in here in these units so that you use meters here. This way it's more explicit because we've worked out the numbers and we see that because G is in meters in this equation, then we have to use it for R.